Hello everyone. Today I will present our recent progress on this research named Understanding the Mechanisms behind NDT-Based Localization Vulnerabilities in Autonomous Driving. I am Yuna Tanaka from WasedaUniversity and Deloitte Tohmatsu LLC. Accurate localization is essential for autonomous driving. Localization errors can lead to dangerous driving behaviors such as lane departures, ignoring traffic signs, and collisions. I will explain the process of matching the pre-built point cloud map with the real-time LiDAR scan. First, the GNSS provides rough position estimate. Then, high-precision localization is achieved by aligning a pre-built map with a real-time LiDAR scan using normal distribution transform NDT. Here, the blue points are the point cloud manipulated by the attack. Such manipulation causes autonomous vehicle to misestimate its position. As a result, the HD maps traffic sign locations no longer match the real world, potentially causing the vehicle to ignore important signs. This slide presents an overview of the localization system. High-precision localization is achieved by combining multiple sensors, such as LiDAR, GNSS, IMU, and vehicle speed. NDT scan matching aligns the real-time LiDAR scan with the pre-built map using GNSS rough estimate. IMU and velocity data are used to achieve stable localization. These data are fused by IMU odometry fusion and then input into the extended Kalman filter, EKF. EKF fuses the NDT estimated pose with twist information to proceed a more stable estimated pose. This output is then used for the next frame's NDT. Previous researches have demonstrated attacks on localization, but these studies have several limitations. First, point cloud manipulations are heuristic and lack a systematic analysis of NDT vulnerabilities. Second, attack evaluations do not consider sensor fusion with IMU or velocity data. Third, these evaluations do not include driving scenarios, particularly the impact on AV planning and control. In contrast, our research addresses these limitations. First, we analyze the fundamental vulnerabilities of NDT and introduce an attack that strategically manipulates LiDAR scans. Second, we evaluate the impact of EKF sensor fusion on the attack effectiveness. Third, we demonstrate through end-to-end evaluation that localization errors can lead to dangerous driving behaviors. I will explain the NDT algorithm and the vulnerability. The following iterative process is performed until convergence. First, for each real-time LiDAR point, the neighboring voxel is in the pre-built map is searched. For the found voxels, the alignment score, gradient, and Hessian are calculated and summed. Finally, the next transformation vector is determined and applied. Here, if no neighboring voxel is found for points, that point is excluded from the score calculation and do not affect the transformation. In this figure on the right, many points are injected in the middle of the road, but since no neighboring voxels are found, they are ignored by NDT. Therefore, to exploit the vulnerability of NDT and induce localization errors, adversarial point clouds should be injected near regions corresponding to the pre-built map points. To induce significant localization errors, it's effective to gradually shift the point cloud structures present in the pre-built map. This causes the errors to accumulate and can also deceive the neighboring search. In this figure, by gradually shifting the blue injected points, the estimated pose gradually move forward. This is a demonstration movie of the attack. On the left, the vehicle is stopped. The ball is gradually moving. This represents the injected points. On the right side is the localization result. The injected points consistently match the pre-built map. Although the autonomous vehicle is actually stopped, the estimated pose is drifting forward. In practice, such manipulation can be achieved by spoofing or physical object placement. Now, let's move to the attack evaluation. First, in scenarios where the autonomous vehicle stopped, we evaluate the impact of point cloud manipulation on the NDT estimated pose and EKF fused pose. We used AutoWare with OSIM and our VLP16 LiDAR. We tested 4 scenes: Metropolitan, City, Rural 1, and Rural 2. First, we identify effective manipulation areas for inducing errors in each scene. Next, we move the Unity object at 0.1 meter per second to simulate point cloud manipulation. Then, we measure the Euclidean distance between the estimated poses in benign and attack cases. The experiment was conducted 5 times with and without Swift fusion. For each scene, we show the identified effective point cloud manipulation areas. We found that the manipulation area is larger in complex environments surrounded by tall buildings and small in open areas. Here, we show the average and standard deviation of the maximum localization error distance for each scene. We confirmed that the shifting distance of the manipulated points matches the resulting localization error. Therefore, by stopping the shift at any position within the maximum localization error range, an arbitrary error distance can be induced. I will explain this table. The horizontal manipulated angle is below 183 degrees in all scenes, which is achievable using existing spoofing techniques. Without Swift fusion, the maximum localization error reaches 23 meters. With Swift fusion, error of 12 meters occurred. While EKF Swift fusion mitigated the error, it still exceeded 7 meters. Next, I will explain the end-to-end evaluation. We evaluate the impact of AV planning and control. The scene used is Metropolitan. The starting point is set at this location, and the goal position for the right turn and left turns are set at the star marked positions. We move the Unity object to induce a 5-meter error during right turns and a 6-meter error during left turns. Considering the stop line position and lane width, this error distance was chosen to induce critical failures. This slide shows the result of the end-to-end evaluation. The white line is trajectory without the attack, and the green line is trajectory with the attack. The autonomous vehicle misinterprets its position as being ahead of its actual location. This shortens the perceived straight line distance to the turn, causing the autonomous vehicle to enter the opposing lane during right turn and mount the sidewalk during left turns. This can lead to serious accidents. Next, I will explain the defense method, robust NDT scan matching. It's based on the idea that since the attack modified only a portion of the point cloud, excluding the affected point may help mitigate its impact. First, the real-time LiDAR scan is divided into several subsets. Next, NDT is performed on each subset. Finally, the estimated pose from each subset are compared and the most suitable one is selected. Implementation and evaluation are left as future work. I will discuss the future directions of this research. First, generalizing the attack success conditions across various environments and optimizing point cloud manipulation are key areas. Next, evaluating the feasibility of the attack in the physical world using LiDAR spoofing or physical object movement is another direction. Additionally, we plan to implement defense methods and evaluating their effectiveness. In summary, we analyzed the vulnerability of NDT and demonstrated an effective attack method. That concludes my presentation. Thank you very much.